In order to develop a polar equation of a conic section, we're going to start by considering a conic section with a focus at the origin. So that's what I have here. It's a generic conic section. We don't know if it's a parabola, ellipse, or hyperbola. As you can see, the focus is at the origin. And all conic sections have a directrix. Up till now, you've probably only seen the word directrix in association with a parabola. But what we have is, at the bendiest part of whatever the conic section is, inside that bendy part is a focus, and on the opposite side is the directrix. I'm going to label the directrix L, and it has an equation we're going to say is x equal to d because it's a vertical line. Our goal is to develop an equation for the conic section in polar coordinates. So what I'm going to do is identify a point on the conic section, I'll call it P, and we're going to consider two distances. One is the distance from the focus to the point. Because the focus is at the origin, when we think of this in polar coordinates, that distance is going to be r. Since r is the distance from the point F, which is the focus, to the point P on the curve, we're going to say r is equal to, it looks like absolute value pf, and it means the distance between the 2 points F and P, but that distance is of course r. There's a second distance that we're going to consider. It is the perpendicular distance between the point P on the curve and the directrix. We're going to call that distance PL in absolute value looking thing. And it just means the distance between P and L. In order to come up with an expression for the distance PL, it would be useful if we had an x-coordinate for the point P. And we do. In polar coordinates, the x-coordinate of a point is given by x is equal to r times the cosine of theta. The distance that we've just denoted x is actually going to be the distance from the y-axis to the directrix minus the distance from the point to the directrix. So the distance PL is equal to, now the distance from the y-axis to the directrix is d, and the distance from the y-axis to the point P is the x-coordinate. So PL is equal to d minus r times the cosine of theta. We talked before in the context of ellipses about eccentricity, and now we have a more general idea of eccentricity. The distance PF divided by the distance PL is actually defined to be E, the eccentricity. And be aware here that E does not stand for Euler's number, 2.7. It's the eccentricity. So it's just E for eccentricity. But now this is a definition of E for all conic sections. But we can start replacing some of the expressions in this equation. PF is actually R. L is D minus R times the cosine of theta. So we get the equation r divided by d minus r cosine of theta is equal to E. Clearing the fraction gives us that r is equal to ED minus ER times the cosine of theta. And at this point, what we're after is an equation where r appears on one side and everything else is on the other. Here I have r on both sides. So collecting r onto one side, we get r plus ER cosine of theta is equal to ED. And by factoring out r and then dividing, we get r is equal to ED divided by 1 plus E times the cosine of theta. This is the equation of a horizontally oriented conic section. And we know it's horizontally oriented because when we developed it, we had a vertical directrix and this curve was opening to the left. Now, again, we don't know what happens beyond that, but we have this curve that opens to the left. So let's flesh some of this out. This is the equation of a horizontally oriented conic section. The directrix has an equation x is equal to d, as we saw. If our directrix had been on the other side of the y-axis and so existed on the negative y-axis as a vertical line, then this expression on the right-hand side would change. We would have 1 minus E times the cosine of theta, and the directrix would have an equation x is equal to negative d. That we have a cosine expression in the equation, it shouldn't be surprising because here we have our conic section that's oriented so that it is symmetric with the polar axis. In order to see a conic section that would be symmetric with respect to the line theta equals pi over 2, that would mean we would have a horizontal directrix, and that would result in a vertically oriented conic section. So the equation of a vertically oriented conic section is r is equal to ED divided by 1 plus E times the sine of theta. It's identical to the previous one, except that there's a sine instead of a cosine. The directrix would be aligned with the equation y equals d. And as before, if this was 1 minus E times the sine of theta, then the directrix would have equation y equals negative d. Now, this is great. We have two equations, or really four if you consider the plus or minus. For a conic section, if I see an equation that looks like this, either one of these with a sine or a cosine in the denominator, then I know it's a conic section. But which one is it? I told you this was a generic conic section. We didn't know if this was a parabola, ellipse, or hyperbola. The number E is what's going to tell us this. So E indicates which conic section we have. I'll write down a reminder of what E is. It's the distance from the point on the curve to the focus divided by the distance from a point on the curve to the directrix. And that's what E equals. Going back to our picture, if the distance from the point to the focus is the same as the distance from the point to the directrix, then that's what actually defines a parabola. And so if E equals 1, we have a parabola. You may recall from our discussion about ellipses that if my foci are very far apart from the center, then I have an eccentricity that's approaching 1. And for an ellipse that's more circular, the distance between the foci are getting closer, the eccentricity would be approaching 0. Here's the point. The eccentricity for an ellipse is less than 1. Finally, if E is greater than 1, then we have a hyperbola. And that means that the distance from the point to the focus would be greater than the distance from the point to the directrix. So here's what some of our work is going to look like. If we have a function that looks like r is equal to c over a plus or minus b times the sine of theta or cosine of theta, then the first thing that we need to do is take the first term in the denominator, which I've written as a, and make it 1. Of course, we don't do that with an eraser. We do that by dividing all terms by a in the numerator and denominator. After dividing, then the number that is now in place of b, it'll be b over a, becomes e. And knowing what e is tells me which conic section we have. The number in the numerator, so I'll call this the third step, becomes ed. And if I know what e is, and I know what the number c was when we started, then I know what d is. And if I know what d is, folks, then I know the distance between the focus and the directrix. As far as graphing, and that's part of what we're going to do, I would recommend setting up a theta r table, and at minimum, plot the points that are associated with theta equals 0, pi over 2, pi, and 3 pi over 2. Figure out what r is, plot the points. You already know what the shape is because you know what e is. And there you go.